The first reaction that we covered in the video is reaction of alkenes with hydrogen halides, HBr, HCl, HBr, and HI. Can you hear me?
Yes.
Yeah, and you can see the board, right?
Yes. Yes.
This is an alkene. And no, this is an alkene. And I will add, for example, HCl. And we know that pi bond can act as both base and a nucleophile, right? So here, pi bond will act as a base. It will break, and both electrons will form a sigma bond between one of the sp2 carbons, either A or B, and hydrogen. And no bond between hydrogen and chlorine breaks. So let's add hydrogen to carbon A. Does it make any difference if I add hydrogen to carbon A or B in this case for this alkene?
No, because it's symmetrical.
No, because it's symmetrical, okay? So these two electrons, this sigma bond, was previously the pi bond between A and B, okay? So pi bond breaks, and both electrons will form a sigma bond with the hydrogen. Now the other carbon, in this case B, will have 3 bonds and a positive charge. So a carbocation forms. Any questions so far? And then chloride will act as nucleophile, and it will attack the carbon with positive charge, and we get the final product. This is hydrohalogenation. So if you have a symmetrical alkene, it doesn't make any difference if you add the hydrogen to carbon A or B. But what if we have asymmetrical alkene? Like this one. Again, we have carbon, this is carbon A and carbon B, the sp2 carbons. And then we add, again, HCl. And pi bond will break and form a sigma bond with one of the carbons, and hydrogen, chlorine leaves. Now, we can add hydrogen to carbon A. And you know that carbon A already has a hydrogen, right? This is bond line structure. So we can add hydrogen to carbon A, and carbon B will have a positive charge. Or we can add hydrogen to carbon B. Carbon A will have a positive charge, okay? So these two carbons are different. A has more hydrogens than B. A has 1 hydrogen, B doesn't have any hydrogen. So if we add hydrogen to carbon A, the sp2 carbon with more hydrogens, we get a tertiary carbocation. If we add hydrogen to carbon B, sp2 carbon with fewer hydrogens, we get, what type of carbocation is this? Write it down. It's a secondary. Which one is more stable? Tertiary, okay? So which one forms faster? Tertiary. And there will be more tertiary carbocation than primary. So the major product will be this after chlorine attacks. And this will be the minor product. This is the major. And this is the minor. And when hydrogen adds to carbon to sp2 carbon with more hydrogens, that usually gives us the more stable carbocation. We call this Markovnikov addition. Because Markovnikov, a Russian scientist, discovered that in general, hydrogen tends to add to sp2 carbon with more hydrogens, and nucleophile adds to carbon to sp2 carbon with less hydrogens, with fewer hydrogens. And the reason is what you see here. Usually when you add hydrogen to sp2 carbon with more hydrogens, the more stable carbocation forms. Do you have any question? So this is the Markovnikov product, and the other one is product of anti-Markovnikov addition. And in the video, I told you how to make the anti-Markovnikov the major product. What you should do, what reagent do you need to use to make the anti-Markovnikov the major product?
Peroxide.
You mix your hydrogen halide with peroxide, ROOR. And the reason is that it will change the mechanism to radical, and we will cover that in the future chapters. But now, right now, you still need to note this for the exam, okay? So this is the alkene. Give the major product for both reactions. Which one is the major product of reaction, top reaction with HBr? So A is the major product of the first reaction. And which one is the major product of the second reaction, the one with HBr and ROOR, peroxide? B. Good. Any question? Okay, this reaction, same thing. We have an alkene. Is it symmetrical or asymmetrical?
Asymmetrical.
Asymmetrical. So pi bond will break and forms a sigma bond with the hydrogen, and I call it A and B, okay? Should I add hydrogen to carbon A or to carbon B? To carbon A, carbon with more hydrogens, good. So first, this carbocation forms. I'm not showing the hydrogens which are bonded to carbons, but I have added a hydrogen to carbon B, right? So before the reaction, it had 2 hydrogens. This one had 1 hydrogen. After adding the hydrogen, A has 3 hydrogens and B still have 1 hydrogen. Now, when there is a carbocation, what is possible? Rearrangement, right? Good. So I can shift this metal group over there, and the secondary carbocation becomes a tertiary carbocation. Which one is more stable? Tertiary, so it will undergo rearrangement, and there will be more tertiary carbocation than secondary because tertiary is more stable. And then bromide will attack both carbocation, but the major product will be this. This is one of those examples that the anti-Markovnikov product probably doesn't form at all because that's a primary carbocation. If it forms, it will completely be converted to the secondary and then tertiary, okay? So probably these will be the only 2 products. But since these are experimental, I probably won't ask you to predict if there will be any anti-Markovnikov or not. Usually I will ask you to give the major product or give all the possible products and identify the major product. Any question? Are you guys there? Can you hear me?
Yep.
Yes, we can hear you.
Okay. Any question for hydrohalogenation? No? Okay, now when this product, the major product, forms, what happens if I add methoxide? What will be product if I add tertiary methoxide? We have alkyl halide and we add a strong base. E2 and SN2. Which one is the major in this case? E2. And is the product for methoxide, product is Zaitsev or Hoffman. Z for Zaitsev, H for Hoffman. Zaitsev. So this is the major product of the first reaction. And second reaction, is it Hoffman or Zaitsev? Hoffman. And how about the minor product? if I add methoxide or tertiary butoxide, what do I get? You can turn on your microphone and tell me.
Can you repeat the question?
For the minor product, for this product. Let me go to the next slide. This was the minor product of that reaction, right? Now, if I add methoxide, if I add tertiary butoxide, give the product, the major product. Do we get different products for methoxide and tertiary butoxide? It's E2 again, but same product for both. That's right. So because look, this is the alpha carbon. There are 2 beta carbons, but the beta carbon on the left side doesn't have any beta hydrogen. So only one product is possible, which is the same as the reactant that we used. Now, what if I add HBr and H2O2 to this compound? What do I get? Which one is the major product of this reaction? HBr and hydrogen halide and peroxide is the reagent that we use for anti-Markovnikov addition. So the major product will be C, as you said.
Will we likely be using H2O2 in terms of peroxide, or would it be any like ROOR?
Yeah, you use either H2O2 or ROOR, R2O2 for
Okay.
for exam. Yeah.
Just so I recognize it. I mean, I would be able to recognize it, but if it's usually H2O2, then I'll recognize it better.
Yeah. Well, depends. Sometimes it's we use ROOR or
Right.
R2O2.
Okay.
No, I never use R2O2 actually. It's ROOR or H2O2. Hydrogen peroxide is an example of it, peroxide. Okay. Any question for hydrohalogenation of alkenes? No? Okay, the next reaction that we will investigate is hydration of alkenes. Hydration means adding H2O, components of H2O to the molecule, okay? Components of H2O is a hydrogen and an OH. This is H2O. But when we're doing hydration of alkenes means we add hydrogen to one sp2 carbon and OH to the other sp2 carbon. If we have an alkene and we add just H2O and we wait and wait and wait, nothing will happen. We need a catalyst for this reaction. And the most common catalyst that we can use is acid. So we can add few drops of sulfuric acid, for example. This is the most common acid that catalyst that we use for hydration of alkenes. So we can use H2SO4, I will show that H+, and sometimes you will see H3O+, this is the same thing, or H2O, H2SO4. These are all the same thing, okay? They all do the same. Okay, here pi bond is the base again, and protonation of pi bond. So we add hydrogen to one of the sp2 carbons and a carbocation forms. Again, Markovnikov addition gives us more stable carbocation. So I will add hydrogen to carbon A or B. To carbon A because A has more hydrogens. And this carbocation will form. So I added hydrogen to carbon A. Why I'm not showing that hydrogen? Because in bond-line structures, we don't label the carbons or hydrogens which are bonded to carbons, okay? But we know that right now there are two hydrogens bonded to this carbon that we don't show. And here there's one hydrogen bonded there, but we don't show them. The next step, H2O will act as a nucleophile and it will attack this carbon with positive charge. So this arrow means that a new sigma bond forms between lone pair of oxygen and carbon with positive charge. Are we done here? No, we cannot have oxygen with 3 bonds and a positive charge. It's not stable. So another H2O molecule will remove this hydrogen. So the last step is a proton transfer. And this is the final product. Final product of Markovnikov addition. This is the final major product. Question. No question? Can you hear me?
Yes.
Yes.
Okay, good. So hydration of alkene gives us an alcohol, right? So we add H2O and H2SO4. It's like dilute H2SO4 because it's mostly H2O and few drops of H2SO4. Do you remember dehydration of alcohols? So when you have an alcohol, you add concentrated H2SO4 and heat, and what happens? What's the product?
Alkene.
An alkene forms. And you know the mechanism of reaction. If you have secondary or tertiary alcohol, mechanism of reaction is E1. So carbocation forms, carbocation rearrangement is possible, and then a proton transfer gives an alkene. If you have a primary alcohol, it is E2. So if we have an alkene, now let's go to the next slide. Dilute H2SO4 means water with few drops of H2SO4. This becomes alcohol. And then you can convert that alcohol with concentrated H2SO4 and heat to the alkene. So these two reactions are opposite of each other. Can you tell me what reagents do I need to use to convert that alcohol to this alkene?
A weak base and weak liquid.
When you're doing H2SO4, that's what you're doing, weak base. First, you have to convert your OH to a, because this is the Hoffman product, right? This is Zaitsev product. When you go from the alcohol to this is Zaitsev. This one is Hoffman. How do you do that? Step one, I will convert OH. So you cannot use H2SO4 or anything that encourages E1. So I can do tosyl chloride. If we add tosyl chloride, OH becomes what?
OTS.
Becomes OTS, great leaving group. And then when OH becomes OTS, so it becomes this. OTS. And you want a Hoffman product. Let's substitute an alkene. What do you use in the next step?
Bulky base.
Bulky base like tertiary. Question? Nope. Give the major product of this reaction. Oh, I'm sorry, not this reaction. This is hydration. Hydration of this alkene. Can you name this alkene?
It's 2-butene. 1, 2, 3, 4.
It's
Wait.
2-methyl.
Oh, 2-methyl-1-butene.
2-methyl-1-butene. Good. Now, after hydration, what is the product? So first the carbocation forms, and then what type of carbocation forms?
Tertiary.
Tertiary, and then OH will be attached to that tertiary carbon. So this is the major product, right? So after this reaction, did any new chiral center has formed in this reaction in the product?
Okay.
Can you see any?
When are you leaving? Oh, I'll see you tonight. If not,
You cannot hear me?
Yes, we can hear.
okay. Have a good trip.
So is there any new chiral center in the product?
No.
No? Oh yeah, you're right. Okay, sorry. So that was the wrong example. How about now?
Yes.
Yes, there is a new chiral center in the product, right? And do you think that one enantiomer forms more than the other, or we will get a racemic mixture? And why?
I think it should be racemic because the carbocation is flat, so we can either attack from the front or back.
That's right. So when the carbocation forms, this carbocation forms, and H2O can attack from either side, from front or from the back. And we get mixture of both enantiomers, okay? So we get a racemic mixture. Remember, it was the same for hydrohalogenation. If a new chiral center forms in the product is racemic, because again, carbocation is planar, it's flat, and nucleophile can attack from either side. Can give you the R or S enantiomer. Question? Okay, for hydration of alkenes, there are 3 different reactions that you need to know. Okay, so we have an alkene, and you want to convert it to alcohol, hydration. The first reaction that you need to know is reaction of alkene with H2O and acid. The second one is called oxymercuration, demercuration. And this is a two-step reaction. Step one is oxymercuration. And step two is demercuration. And sometimes the demercuration step is called oxidation. And the third one is, again, a two steps reaction, hydroboration. Oxidation. Okay, so the first reaction with H2O and acid. The major product is Markovnikov or anti-Markovnikov. Write it down. Markov, M for Markovnikov, AM for anti-Markovnikov. Can you hear me? Okay. So product of this reaction, so if you have an alkene, you add H2 and acid. Major product is Markovnikov. So this is a Markovnikov addition. Is carbocation rearrangement possible or not? Yes, because intermediate is a carbocation. And hydrogen and OH they add to the double bond from one side, opposite sides, or both? Remember, a carbocation forms and then OH can attack from either side, so it's both, right? And we say it's syn and anti addition. Syn addition means hydrogen and OH will add to the same side of the double bond. Anti-addition means that hydrogen and OH will add to opposite sides of the double bond. And since there is a carbocation, both are possible. Any questions so far? When we say it's Markovnikov addition, what does it mean? I forgot.
The hydrogen bonds to the one with more hydrogen.
Hydrogen adds to sp2 carbon with more hydrogens. Good. Okay, the next reaction, oxymercuration, demercuration. Reagent is step one. HgO C2 with H2O. And step two is sodium borohydroxide, NaBH4. Sometimes we call this reaction oxymercuration reduction, because in the second step, NaBH4 will reduce the product. In oxymercuration, demercuration, product is Markovnikov. The major product is Markovnikov. This is a Markovnikov addition. Carbocation rearrangement is not observed, no rearrangement. It is anti-addition. And I will go over the mechanism in a few minutes. And the third reaction, hydroboration oxidation. Guys, do you have any question?
No.
No. Step 1 is BH3 THF. This is the hydroboration step. And step 2 is H2O2 hydroxide and H2O. Hydroboration oxidation is anti-Markovnikov addition. The product is anti-Markovnikov. There is no rearrangement. And it's a syn addition, which means hydrogen and OH will add to the same side of the double bond. And we will go over the mechanism of action. Okay. In oxymercuration, step 1, reagent is HgOAc2 and H2O. In the first step, pi bond will act as a nucleophile and attacks the Ag. And we expect a carbocation form, but the actual intermediate of this reaction is this. Since Hg, mercury, is a large atom, it can overlap with both carbons. And a three-member ring forms, okay? And this is more stable than a carbocation because both carbons are octet in this intermediate. And this is mercurinium ion. Now there is no carbocation. So do you think it can undergo carbocation rearrangement?
No.
No, when there is no carbocation, there is no carbocation rearrangement. So this is the actual intermediate of this reaction. And there are two, in this case, it's not symmetrical, right? I call the carbons A and B. So there is actually partial positive charge on both carbons. And which one can stabilize the partial positive charge more, A or B, and why? What type of carbon is A? Is it primary, secondary, tertiary? What is A?
Tertiary,
It's a tertiary. And how about B?
secondary,
Is secondary. Carbon A is bonded to 3 other carbons, so it is tertiary. Carbon B is bonded to 2 other carbons, so it is secondary. And we know that tertiary carbon stabilizes the positive charge more than secondary. So actually there is more partial positive charge on A. And sometimes we draw the intermediate like this. So we show the bond between the more substituted carbon and the Hg as a partial bond. So it's like it's already breaking. Now, there is more partial positive charge on the more substituted carbon. So nucleophile will be attracted to carbon A or to carbon B.
A,
A, why?
because it has partial positive charge.
Because it has more positive charge than this. So it will attack here from below. So the one side of this intermediate is blocked by Hg, right? The nucleophile can only attack from the opposite side, from below. And that's why we call it anti-addition. So nucleophile attacks from here and now bond between carbon A, more substituted carbon, and Hg will break on Hg. And this will form. And in the next step, we add sodium borohydride. And sodium borohydride will replace HgOHC, this, with a hydrogen. The mechanism is very complicated. We will cover it in Orgo 2, but not now. And this is the product. So as you can see, mechanism of reaction is Markovnikov, because eventually we added hydrogen to carbon to sp2 carbon with more hydrogens, and nucleophile to sp2 carbon with less hydrogens. Now, if nucleophile is H2O, the product will be an alcohol. What if nucleophile is an alcohol? What will be the product? Let's say nucleophile is H2O first. Deprotonation becomes OH. And then sodium borohydride, this is a step 2. It becomes alcohol. Okay. Now, what if instead of, do you have any question so far? Can you hear me?
Yes, we can hear you.
Okay. So what if instead of H2O, I add an alcohol? What's the final product? What is this?
Ether?
Ether, yeah. Product will be ether. So in oxymercuration, demercuration, if in the first step you use H2O as nucleophile, product will be alcohol. If you use alcohol as nucleophile, the final product will be an ether. So now we know why the mechanism of reaction is Markovnikov, why there is no rearrangement, and why it is anti-addition. Any question? No question? Hello?
We're still here.
You don't have any question?
No.
Okay. Okay, now give the major product of these reactions. What is the major product of the first reaction with H2 and H2O and acid is the reagent? Okay, I have 3 answers. 4, 5, 6, 7, 8, 9, 10. Okay, so the answer is C. Why? Because a carbocation forms first, and then carbocation will undergo rearrangement, becomes tertiary carbocation, which is more stable, and that gives the major product. How about the second reaction? What is the major product of the second reaction? We know that with oxymercuration, demercuration, it's Markovnikov addition, no rearrangement, and it is anti-addition. Just one person. 2. I only have 2 answers. B, okay. Good. So the answer is B. It's Markovnikov. You add hydrogen to carbon with more hydrogens, and OH to carbon with less hydrogens. No rearrangement. Anti-addition. Question. If you have question, turn on your microphone and ask your question.
Can you re-explain when you say anti-addition what you mean? Because it's not anti-Markovnikov, sorry.
Oh, yeah. I mean, hydrogen and OH will add to opposite sides of the double bond because of that, because of this intermediate. This is what I mean.
Okay, I just wanted to make sure I was
Yeah.
on the right page with you.
Because nucleophile, whatever it is, has to attack from the opposite side of the Hg. Hg is blocking one side of the molecule, one side of this species, and nucleophile has to attack from below. So eventually, it's like we have added the nucleophile and hydrogen to opposite sides of the double bond. That's why we call it anti-addition. But it's different from anti-Markovnikov. It's a different.
Great, thank you.
This is for stereochemistry.
Do you suggest us to know all the intermediate steps or just the final product?
Yeah, know the intermediate, know the mechanism of reactions. Because usually if you don't, you give the wrong product. And sometimes I will ask you in the exam, what is the intermediate of this reaction? Okay, the next reaction for hydration of alcohol is hydroboration oxidation. In hydroboration oxidation, reagents are step 1, BH3THF. THF is just solvent. And step 2 is H2O2, NaOH, and H2O. And product is anti-Markovnikov, which means we add hydrogen to carbon with less hydrogens and OH, nucleophile, to carbon with more hydrogens. So this is the major product of this reaction. You look at the sp2 carbons. This carbon has 1 hydrogen, the other one has 2 hydrogens. So in anti-Markovnikov, we should add hydrogen 2 carbon with less hydrogens, with fewer hydrogens, this carbon. And OH, 2 carbon with more hydrogens, this one. Question? So this is anti-Markovnikov addition. There is no rearrangement. And it is a syn addition. What does it mean? It means that hydrogen and OH will add to the same side of the double bond. For example, if we have this alkene and we add BH3THF and then H2O2 NaOH H2O. Hydrogen and OH will add to the same side of the double bond. It's a syn addition. Okay, so we can see it better when the reactant is a ring, it's cyclic.
Why don't you call it cis instead of?
Because cis is the product is cis, but the addition is called syn.
Oh, okay. That's more like a process.
Yeah, exactly. Question? Now, why it is a syn addition? And of course, it's pair of enantiomers. Let me show you the intermediate of this reaction. This is an alkene. Is it symmetrical or asymmetrical?
Asymmetric.
Mhm. And if I call them A and B, with hydroboration oxidation, should I add OH to A or B?
A.
To
A.
B. Hydroboration oxidation is anti-Markovnikov. So hydrogen adds to A and OH will add to B. Now, what is the mechanism of reaction? This is BH3. THF is the solvent of reaction. And this is a concerted reaction. So pi bond breaks and starts to form a bond with borane. And one of the hydrogens will start to form a bond with carbon A. The pi bond is breaking. A new sigma bond is forming with borane. Bond between borane and one of the hydrogen is breaking. And a new sigma bond is forming between that hydrogen and the more substituted carbon. In this transition state, there is partial negative charge on borane and partial positive charge on this carbon. Why do I call it transition state and not intermediate?
Because there are bonds that are forming and breaking.
Mm-hmm. Good. Now, can you draw the other transition state? Add boron to the more substituted carbon and hydrogen to the less to hydrogen carbon with more hydrogens. So draw the other possible transition state when boron starts to form a bond with A and hydrogen starts to form a bond with B. And tell me which one is more stable, this one that I have here or your transition state. And this sign over here called double dagger, and we use it for transition state of reactions. Did you draw it? Who has the second transition state, the other possible transition state?
I think I have it.
You have it? Do you think it is more stable or the one that I have it on the board? If I call
Well,
this 1 and we call yours 2, which one is more stable, 1 or 2?
Well, I think the second one, because boron is bonded to tertiary carbon.
And now positive charge is where?
Oh, the positive charge is on the primary carbon.
Yeah. So which one is
Okay.
more stable?
The first one.
This one. So the other possible transition state is this, and I will draw it with yellow. And I call this one 2. Now you guys look at these two transition states. Partial, and check the partial positive charge. And tell me which one is more stable, 1 or 2?
How did you know which carbon has the partial positive charge?
Because pi bond is breaking and forming here, boron B has an empty p orbital, so it's acting as an electrophile here. So pi bond breaks and starts to form a sigma bond with that boron, but the other carbon will have positive charge, and it has to form a bond with hydrogen. So if we don't draw that, this is what happens. Boron is similar to carbocation. It's not octet, it has an empty p orbital. So this pi bond will break and forms a sigma bond with boron, and the other carbon, which is, for example, this one, will have a positive 3 bonds and a positive charge. That's how we know. And then the hydrogen will start to form a bond with that carbon with positive charge. Did I answer your question?
Yeah, thank you.
Yeah, because it will be something like this. Okay, in the next step, when this transition state forms, so this is less stable, and this one is more stable. So we don't want the less stable one. And then the transition state becomes this molecule. And then the other hydrogens of boron also will be replaced with the alkyl groups. And then the next step, we add hydrogen peroxide and H2O. Okay, here. Now, can you tell me why it is syn addition? Look at the mechanism of reaction and transition state and tell me why. In transition state, you're adding boron and hydrogen at the same time to the same side of the double bond, and this is called syn addition. Syn addition. And later, boron will be replaced with OH. Can you hear me?
Yes.
Yes.
So everybody understands why it is syn, we call it syn addition? Why it is a syn addition? Because in the first step, boron and hydrogen add at the same time to the same side of the double bond. So eventually the product will be cis, syn. And you can see mechanism of oxidation when we add H2O2 and hydroxide. You can find it in the PowerPoint slides. You can take a look at it and eventually you will have the alcohol. The final product is alcohol and the product is anti-Markovnikov. Question? No question? Give the product, the major product. Should I add hydrogen to carbon A or B?
A.
To carbon A and OH to carbon B. The major product is this. This is anti-Markovnikov addition. Is a new chiral center formed in this in the product?
Yes.
Yes, this carbon. And do you think it will be R as, I mean, one, this enantiomer or the other one, or racemic mixture, both?
Is it just one?
Is it just R?
I don't know. I'm asking
It is
you.
R.
So you can add OH and H to, you know, the double bond is planar, right? So
Oh, so
you
it could be
can,
both sides.
yeah, it can be both.
Okay.
So you can add them on from, for example, top, or you can add both from below. So we get a mixture of both enantiomers.
So this doesn't have to do with like the syn addition part.
No, no, it's not. Syn means hydrogen and OH both add to the same side at the, yeah, actually it does, because you're adding both at the same time to the double bond, which is stable, which is planar. So you can add both at the same time from top, or you can both add both from below. Question?
How would that work if it was in a ring? Could you do the same? Like, would it still be a pair of enantiomers?
Yep. If a new chiral center forms, yes. Give the final product. Call it A and B. Should I add hydrogen to A or to B?
B.
To B. And OH to A, right? So I have to add OH to A because it's anti-Markovnikov. Yeah, anti-Markovnikov. So OH here. And here I have a methyl group and I have a hydrogen. Hydrogen and OH should be on one side because it's a syn addition. And then methyl group and hydrogen on the other one should be on one side, okay? Is there a new chiral center in this molecule?
Yes.
How many?
2.
2, right? And you can add hydrogen and OH from top or from below. So again, we get pair of enantiomers.
Is that
Cool.
always the case, or do we have to look into?
If a new chiral center forms after the addition.
Okay.
Who asked for a ring? Someone asked if I can show a ring.
Oh, I did.
Did I answer your question with this example?
Yes, yes, you did. Thank you.
Oh, and sorry, in this case, we get a pair of diastereomers, not enantiomers, because we have two chiral centers. Mistake. Okay, the next reaction is hydrogenation. And hydrogenation means reaction of alkene with hydrogen molecule. We need hydrogen and a catalyst. Catalyst can be platinum, palladium, or nickel. Mechanism of reaction is not known, but it's a syn addition. Both hydrogens will add to the same side of the double bond, and alkene becomes alkane. It is a syn addition. What does it mean, syn addition?
Both hydrogen will add from the same side.
Both hydrogens will add to the same side of the double bond. Give the major product of this reaction. The answer is A. Because it's a syn addition, so both hydrogens will add to the same side of the double bond, and in the product, hydrogens are cis on one side of the ring, methyl groups are on the other side of the ring. Question.
Actually, you said that the mechanism is not known. What did you mean by that?
They don't know what are the details for the mechanism, but it seems to be this, that hydrogen molecule will break down to hydrogen atoms, and it will sit down on the surface of the catalyst like this. Okay, and then the alkene will get close to the hydrogens, and both hydrogens will add to the same side. Probably this is the mechanism.
Okay, thank you.
So the only type of hydrogenation that you need to know for this class is with hydrogen and nickel, platinum, or palladium. Other catalysts, for example, Wilkinson catalyst or anything else that you see in the book or suggested problems, you don't need to know, okay? Any question? The next reaction is halogenation of alkenes. Halogenation is a key step in the production of PVC. So ethylene is formed from cracking petroleum. Then they will do chlorination of ethylene. And then they do an elimination reaction. They will get vinyl chloride. And then polymerization of vinyl chloride gives PVC, polyvinyl chloride. It's just one application. Halogenation is only practical with chlorine and with bromine. With iodine, it's too slow, and with fluorine, it's too violent. So it's only practical for chlorine and bromine. Halogenation is anti-addition. What does it mean?
They're added to opposite sides.
They add to opposite sides of the molecule. For example, if it's a ring, we get the trans product in this case. Well, halogenation is anti-addition. There is no rearrangement. And let's check the mechanism of reaction. Since there is no rearrangement, do you think the intermediate is a carbocation or not?
Not.
No.
If it was a carbocation, then rearrangement would be possible. But in halogenation of alkenes, carbocation rearrangement is not observed. So there is no carbocation. And there's some evidence that shows the intermediate is something like this. This is an alkene. And let's say it's reacting with bromine. And we know that bromine exists as a dipole sometimes, temporary dipoles. And the pi bond will attack the bromine. And then bromine will share one electron pair to form a sigma bond with the other carbon. And this will form a We call it bromonium ion. And this is more stable than carbocation. So on one side of molecule, for example, top or below, there is a ring with bromine. One side of the ring is blocked by bromine, and this is called bromonium ion. Bromonium ion, and if it's chlorine, chloronium ion, are the intermediate of the reaction, and they are more stable than carbocation. Can you tell me why?
Because bromine has larger structure.
If you have a carbocation like this, let's say bromine adds to one of the carbons and this carbocation forms. This carbon with positive charge is not octet, okay? But in bromonium ion, both carbons are octet, and bromine is large enough, as you said, to overlap with both carbons. Since both carbons are octet, bromonium ion is more stable than carbocation. So there is a bridged intermediate. The bromine is blocking one side of the molecule. Now the other nucleophile, which is bromide, the nucleophile will attack one of the carbons, but which one? Does it make any difference in this case?
No.
No. Joe, do you have a question? You said positive is on bromine. Is this a question, or you were answering my question?
No, yeah, that's just why I thought it was more stable.
Ah, okay. So bromine, we can attack either carbon, but from the opposite side of the bridge. That's why it is anti-addition. So when bromine attacks here, now this carbon will have 5 bonds. This arrow means that a new sigma bond is forming between lone pair of bromide and that carbon. Now this bond between bromine, carbon and bromine with positive charge breaks on bromine. And this is the product. If I show this bromine red, if I highlight it as red, this is the new bromine. Okay, it acts from the opposite side. And that's why the product is, we call it anti-addition. That's why halogenation is anti-addition, because of the intermediate. The intermediate is bridged, and the halogen is blocking one side of the molecule. The nucleophile has to attack from the opposite side. Question? The next reaction is halohydrin formation. Do you remember what's the reagent for halohydrin formation? Write it down. Halohydrin. Halo for halogen, hydrogen for OH. Can you hear me?
Yes, we can hear you.
This is the alkene. Now, if we mix the halogen, bromine, chlorine, or iodine with a nucleophilic solvent, like H2O or alcohol, first the bridged intermediate forms. Now, as nucleophile, there are few bromide ions, which are excellent leaving groups. And there are millions of H2O molecules just because it's the solvent. Okay, so let's say we have like 1,000 bromide and millions of H2O. Bromide is a better nucleophile, but there are much more H2O molecules than bromide. So which one has a better chance to act as nucleophile?
H2O.
H2O. So in this case, H2O will attack one of the carbons from the opposite side of the bridge, and that bond breaks. Are we done here?
No.
No.
No. Deprotonation of that oxygen. And product is halohydrin. Halo for halogen, hydrogen for OH of H2O. Is it syn or anti-addition?
Anti.
Anti-addition. Why?
Opposite sides of the
Mhm.
bond.
Why? Why?
Because of immediate bridge.
Because of the intermediate, right? It's bridge. One side of the intermediate is blocked by the halogen, and nucleophile, whatever it is, has to attack from the opposite side. Question. So in halohydrin formation, do you think there will be any rearrangement, carbocation rearrangement?
No.
Why not?
There's no carbocation formation.
Because there is no carbocation, so no carbocation. No question? Can you hear me?
Yes.
Okay.
Yes.
Okay, the next reaction is dihydroxylation. Dihydroxylation means adding 2 OH to sp2 carbons. For example, if we have ethylene and we do dihydroxylation, we get ethylene glycol. Dihydroxylation can be anti or it can be syn. What does it mean, anti-dihydroxylation?
Both oxide,
OH?
OH attacks to the opposite sides.
The final product, the hydroxyl groups will be on opposite side, will add to opposite sides. In syn dihydroxylation, hydroxyl groups OH will add to the same side of the double bond. For example, here, with anti-dihydroxylation, product will be a trans diol. Reagents that we need for anti-dihydroxylation. Step 1, a proxy acid, RCO3H. Step 2, acid and water. It's a 2-step reaction. When we add peroxy acid in the first step, an epoxide will form. And then H2O will attack one of the carbons from the opposite side. Now, can you tell me, when look at the intermediate is epoxide. Can you look at the intermediate and tell me why it is anti-addition?
Because it's a bridge.
Because again, it's a bridge, right? So one side of molecule is blocked by the bridge, by the oxygen. So H2O has to attack from the opposite side, and the final product will be a trans diol. And let me show you the mechanism of reaction. So first, the alkene becomes epoxide. This is peroxy acid. Pi bond will start to form a new bond with this oxygen. This bond breaks. Pi bond forms a new sigma bond with that. This oxygen. Pi bond breaks on oxygen. This oxygen starts to form a new sigma bond with that hydrogen, and this is the transition state. This is the transition state, and then it becomes the epoxide. Epoxide plus carboxylic acid. examples of proxy acids that we can use is proxyacetic acid, and MCPPA, methylchloroproxybenzoic acid. And I think you will see this a lot in the suggested problems. Methylchloroproxybenzoic acid, or MCPBA. So when you see MCPBA in a reaction, you know that it's a proxy acid. Question? So the only thing that you need to know for the first step is the intermediate that forms the epoxide, right? So you should know that if you have an alkene and you react it with proxy acid, product is an epoxide. Question? Can you hear me?
So we don't need to know the mechanism of reaction?
You don't need to know how this transition state forms, how the epoxide forms. You just need to know that alkene reacts with peroxy acid and gives you an epoxide.
Okay.
Okay. So when the epoxide forms, it's similar to bromonium ion. We add acid and H2O. Step 1 is protonation of oxygen of epoxide. The next step H2O will act as a nucleophile and attacks from the opposite side to one of the carbons. After deprotonation, we have the final product, which is a transdiol. Question? So three different, so far we know three different intermediates, bridged intermediates. Epoxide, one with halogen, for example, bromonium ion, and the one with mercury. In all of these, one side of the intermediate is blocked by the bridge, and nucleophile has to attack from the opposite side. And that's why these reactions are anti-additions. Question?
Wait, didn't you said the dihydrosilylation can do syn addition also?
Yeah, we are talking about anti now.
Oh, okay.
I will go over the syn in a couple of minutes. Any question about the anti-dihydroxylation? Okay, in syn dihydroxylation, example here, we will have a cis-diol and there are two different reagents that you need to know for this type of reaction. The first one is osmium tetroxide, and the second one is permanganate. Okay, so you can use either one, osmium tetroxide, OSO4, or permanganate. And we have an alkene, and we add osmium tetroxide. Pi bond breaks, a new sigma bond forms between one of the carbons and oxygen. Pi bond breaks on osmium, the other pi bond breaks on oxygen, and a new sigma bond forms between oxygen and the other carbon. And this intermediate, a cyclic osmate ester will form. So you can see both oxygens will add in one step to the same side of the double bond. In the next step, so the key, the reason that it is a syn addition, syn dihydroxylation, is this intermediate. Both oxygens will add at the same time to the same side of the double bond. And then we add a reducing reagent like sodium sulfide. And this is the product. Mechanism for permanganate is very similar. Do you have any questions so far? This is permanganate. Similar pi bond breaks. Carbon starts to form a sigma bond with oxygen. This pi bond breaks on magnesium. This pi bond breaks on oxygen, and then oxygen forms a new sigma bond with that carbon. So both oxygens will add to the same side at the same time. And this is the intermediate. This is the intermediate. Okay. So manganese, both oxygens bond will add to the same side of the double bond at the same time. And then we add sodium hydroxide. Few steps gives the product. Applications of permanganate is limited. Osmium tetroxide is better because permanganate can react with some other functional groups as well. So usually osmium tetroxide is better than permanganate. Question. So dihydroxylation of alkene can be anti or syn. For anti-dihydroxylation, reaction is 2 steps. Step 1 is reaction with peroxy acid that gives an epoxide. Step 2 is H2O and acid. It gives the final product, which is, for example, here, trans diol. For syn dihydroxylation, we have to use the reagents that you need to know are osmium tetroxide or permanganate. In both of these reactions, both oxygens will add to the same side at the same time. There is one, it's a one-step reaction. Both oxygens will add in one step to the same side of the double bond. And the final product is, in this case, a cis diol. It's a syn addition. If we have a ring, the product is cis. Question. Only one more reaction left. Question. Okay, the last reaction is reaction of alkene with ozone. Ozone will, yeah. Did someone ask a question? Ozone will break down the double bond in the middle. Okay. So you will draw both portions separately. And add one oxygen to each end. So ozone will break down the double bond in the middle, and the products are mixture of aldehydes and ketones. It's very easy to predict the product of reaction of alkene with ozone. Just break down the double bond in the middle and add 1 oxygen to each end. Question? And I'm not showing you the mechanism of reaction. It's too complicated, but you can see it in the PowerPoint slides. It's on Blackboard.
Do we need to know that mechanism of reaction?
No, you don't need to know. Just know how to find the final product. Now, can you give the final product of this reaction? This is an alkene. React with ozone, and DMS is a reducing agent. So for reaction of ozone with alkene, break down the pi bond in the middle, okay, and draw the molecule, the broken molecule again. And add 1 oxygen to each end. So this is the final product, right? These two are the same thing as different conformations. Question? Okay, now let's see what type of reactions we know, we have learned so far. We know substitution reactions. What are substitution reactions? What happens in substitution reactions? We replace one group with another group, right? Another reaction is elimination reaction. You're removing a leaving group and a hydrogen, and a double bond, a pi bond forms between the alpha and beta carbon. We also know addition reactions. We are adding 2 groups to sp2 carbons of the double bond. Actually, double bond, the pi bond becomes 2 sigma bonds. Are you there?
Yes.
Yeah. Now you should be able to use all these reactions for synthesis to prepare different molecules, for example. Give the reagents for this transformation. We have an alkene, product is an alcohol. So you have to, and if I call them A and B, you have to add a hydrogen to carbon A and OH to carbon B. Now, this is hydration, right? It's a simple hydration. And how many different reactions do you know for hydration of alkenes? 3. The first one, reaction of alkene with H2O and acid, right? For hydration of alkene to alcohol. The first reaction that you know is acid and water. The second one is oxymercuration, demercuration. And the third one is hydroboration, oxidation. Now, which one do you think you should use for this reaction, for this transformation?
H3O.
Yeah, we can use acid and water. Can we use oxymercuration reduction? You know that H2 and acid is Markov-Nikov. This one is also Markov-Nikov. This one is anti-Markov-Nikov. So can I use oxymercuration, demercuration for this reaction as well or not? Just
Yes. You can.
yes, okay. So it's either H2 and acid or oxymercuration, demercuration. Either one will work. Can I use hydroboration oxidation as well?
No.
Why not?
Then you will have the OH in A carbon.
Right, because the product will be something else. Give the reagent. Again, this is hydration of alkene, and you know 3 different reagents, okay? I give you 3 different options. A, acid and water. B, oxymercuration, demercuration. C, what's the answer? A, B, C, A and B, B and C, A and C, A, B and C. Which one is the answer? Which reagents you can use? Is it Markov-Nikov or anti-Markov-Nikov?
It's Markov-Nikov.
It's Markov-Nikov. So
A and B.
okay, this is why you need to know the mechanism of reactions. If we do A, step 1, a carbocation will form. And when a carbocation forms, rearrangement is possible. And after rearrangement, we have this, okay? And then final product will be this product, the major product. Is this what you want?
No, so I'm guessing just B then.
So the answer is only B. Because there's no rearrangement in B, and we don't want the rearrangement in this reaction. Question? Give the reagents. Now, since we want the rearrangement, the answer will be A. Good. Question? Give the product of each reaction. Okay, which one is the answer of the first reaction with methoxide? A. Which one is answer with tertiary methoxide? C. Good. So now let's take A. This is A, right? And now I will add HBr. What is the product? I will give you 3 answers. Which one is the answer? The answer is B. Why? Because with HBr, it's Markovnikov addition. you have to add hydrogen to sp2 carbon with more hydrogens, and nucleophile to sp2 carbon with fewer hydrogens. So this is the product, right? And then I will add tertiary oxide to this. Now, which one is the product? I only have 2 answers. Good. So the answer is C. This is the product. And then I will add HBr and H2O2. What is the answer? Is this Markovnikov or anti-Markovnikov addition? So you add hydrogen to sp2 carbon with less hydrogens and bromine to sp2 carbon with more hydrogens. And the answer is this. Okay, so in exam, I can give you this alkyl halide and ask you to prepare this one. And you know how to do this, right? Step 1 is methoxide. Step 2, HBr. Step 3, tertiary oxide. Step 4, HBr and peroxide. Question. And this is called synthesis, right? So you should be able to do these type of questions. Give the reagents for this transformation. Can I do H2O and acid? For these type of questions, there is a technique which is called retrosynthesis, okay? So you start with the final product and you go back. For example, if you want this alcohol, you go one step back. What do you need to prepare this alcohol? You need an alkene, this alkene. Okay? So if you have this alkene, you can do an anti-Markovnikov hydration to prepare that. Now, can you hear me, guys? Are you there?
Yes,
Yes,
we're
we're
here.
there.
Now, to prepare this alkene, can you start with your reactant and prepare that?
Yes.
Yes. How? Can I do H2SO4 and heat? Because from alcohol to alkene, it's dehydration, right? And the first reagent that I remember for dehydration is sulfuric acid and heat. But what will be the product of this reaction? This is alpha carbon, beta. Do I get Zaitsev or Hoffman?
Hoffman,
With H2SO4 and heat.
Zaitsev.
Zaitsev. Because when you have tertiary or secondary alcohol and you do H2SO4 and heat, mechanism of reaction is E1 and major product is Zaitsev. So this doesn't really, I mean, it helps, but we don't want this. You can use this, but no, it will be too many steps. So instead, I'm going to convert OH to OTS. So I will add tosyl chloride and OH becomes OTS. Now, can you give a reagent to convert this tertiary alcohol to that alkene to give the Hoffman product?
Yes.
What is that reagent?
Tertiary butoxide, a bulky base.
Right, tertiary butoxide. And then you can convert this alkene to alcohol. BH3THF and then H2O2 and hydroxide. Good. Question. Sometimes you have to change the position of the pi bond. For that, you have to do a series of addition and elimination reactions. For each addition reaction, you have to decide if you want Markovnikov or anti-Markovnikov. For each elimination, you have to decide if it should be Zaitsev or Hoffman. Okay, let's do retrosynthesis. To prepare that, if we have this compound, this alkyl halide, we can prepare that alkene, right? With Hoffman elimination. Now, can you prepare this alkyl halide using this alkene? Should I add HBr or HBr and epoxide?
The peroxide and HBr.
Why?
That's anti-Markovnikov.
Right, because Look, this is A, this is B, A and B. A has no hydrogen, B has one hydrogen. And in the product, we have added hydrogen to carbon A, the one with less hydrogens, and bromine to B, carbon with more hydrogens. This is anti-Markovnikov addition. And then the next step, you have to decide if you want Hofmann or Zaitsev elimination. Z for Zaitsev, H for Hofmann, decide, type it. One Hofmann, so we add, right, tertiobutoxide, a bulky base. So step 1 is HBr and peroxide. Step 2 is a bulky base. Okay, sometimes it's more than 2 steps, much more. So when you are changing location, position of a pi bond, you have to use a series of addition and elimination reactions. For each addition, you have to decide if it is Markovnikov or anti-Markovnikov. For each elimination, you have to decide if it is Zaitsev or Hofmann. Okay, can you see the slide, this PowerPoint slide?
Yes.
Yeah, these are all the reactions that we learned in this chapter. The first reaction is hydrohalogenation, HX. Is it Markovnikov or anti-Markovnikov?
Markovnikov.
Carbocation rearrangement, yes or no?
Yes.
Yes. Syn or anti or both? Syn addition, anti addition, or both? When there's a
Both.
carbocation, it's both. The second one is HBr, hydrogen halide and peroxide. That product is anti-Markovnikov, and mechanism of reaction is totally different. It's radical. There's no rearrangement, anything. Just know that it's anti-Markovnikov, and that's enough. For hydration of alkene, there are 3 different reactions that you need to know. If you want Markovnikov hydration, you can do either acid and water or oxymercuration, demercuration. With acid and water, there is a carbocation intermediate, so carbocation rearrangement is possible, but for oxymercuration, demercuration, there is no carbocation and no carbocation rearrangement. If you want anti-Markovnikov hydration, you have to do hydroboration, oxidation. For hydrogenation, the reagent that you need to know is hydrogen and catalyst. Halogenation, you need halogen, bromine, or chlorine. For halohydrin formation, you need halogen and H2O as solvent. For dihydroxylation, we can do syn or anti. For anti, peroxy acid, and then acid and water. For syn, either osmium tetroxide or permanganate. And finally, we can we can break down the alkene carbon-carbon double bond to aldehyde and ketones by ozone.